This is a recording of a live, online workshop on time-varying effect modeling, or TVEM. The workshop took place on February 21st, 2017, and was presented by Stephanie Lanza, Scientific Director of the Methodology Center and Professor of Biobehavioral Health at Penn State. The recording consists of a 1-hour presentation, followed by a 1-hour question and answer session, during which Dr. Lanza answers questions posed by workshop participants.
Hi, my name is Stephanie Lanza, and I am pleased to welcome you today to a new format of a dissemination series that the Methodology Center is offering. It's called the Methodology Center 1-in-1, and the idea is that we're going to have an hour, or a little less than an hour today, of a lecture on a statistical method. And today we're going to talk about time-varying effect modeling. And then we'll have an hour open discussion period where Erin will field questions that you submit on your chat window. And so we'll just go through those at a nice pace after I'm finished going through the slides. Really happy to be here today, and we're also interested in your feedback, as Bethany said, on the format of this type of session. So let's see. So just to begin with, I know you can't see me, but I will pop in later when we're doing a Q&A so that you can see me talking with you. My name is Stephanie. I am a professor of biobehavioral health at Penn State, and I am the scientific director of the Methodology Center. And we are largely funded by NIH and the National Institute on Drug Abuse in particular to advance statistical methods for public health research. So again, welcome. We're going to talk about time-varying effect modeling to study developmental and dynamic processes. So first, we're going to just do a little bit of background, sort of how we came to think about TVEM, time-varying effect modeling, and put it to use in the real world. And then I'd like to demonstrate the time-varying effect modeling through two studies. The first study is going to be focused on dynamic change, and want to really focus on nicotine addiction and the process of withdrawal when you quit smoking. So that's going to be a very intensive, dynamic process under study. In study two, I'm going to show a totally different use of the time-varying effect modeling that will have a developmental perspective, and we're going to look at the use of e-cigarettes and traditional cigarettes in adolescents across age. And then I'd like to just kind of conclude with a few thoughts about next steps for TVEM and related methods. Okay, so let's talk about the background to TVEM just a little bit, time-varying effect modeling. Uh-oh, it's auto-advancing. Okay, so first of all, human behavior as it relates to health is dynamic. All right, we're going to turn off the auto-advance. Hang on one second. Oh, here it is. Pilot test. Great. It was going to advance every 5 seconds, and I have much more to say than that. Okay, great. So human behavior as it relates to health is in part dynamic. It's dynamic in many ways, and so this orientation to thinking about human health as dynamic is relevant when we think about behavior change. So how behaviors change across age as we develop and mature, and also how we think about how behavior changes across real time. But in addition to the actual behavior changing across age or time, we may be very interested in changes in processes across age or time. For example, we might be interested in thinking about risk factors for adolescent substance use, but those risk factors may be more salient when you're 12 years old than they are, say, at age 17. And so the time-varying effect modeling approach allows us to unpack this kind of question. And a third reason why I think this dynamic perspective on human health and behavior is really important is that many of us have analyzed data from behavioral interventions, or actually run some of them, and we know that an intervention effect the intervention is on or off, but the effect of the intervention is not black and white. It's not on and it's effective and then it stops working, or it stays working forever. We know that intervention effects are actually dynamic, and they work better for certain individuals of a certain age, and they work as a function of time, real time, whether it's time in terms of minutes or time in terms of years. So let's start with one motivating example, and this is coming back to the smoking cessation study I alluded to. So we know that negative affect, our bad mood, and craving to smoke are tightly linked among addicted smokers. And we know that when addicted smokers stop smoking, they go through withdrawal and hopefully move toward recovery. But this process of recovery is not, it doesn't happen suddenly. You have to go through this process. And we can use time varying effect modeling, or TVEM, to take a closer look at this recovery process. So questions we might use TVEM to answer related to smoking cessation and withdrawal are, is one's negative affect differentially associated with their craving at various points in the smoking cessation process? So you have a bad mood, you get into a bad mood, you want to smoke a cigarette. We know this happens after you quit smoking. But in non-addicted smokers, that effect is absent. And so presumably, when people quit smoking, that link, that association between negative affect and craving to smoke dissipates with time, and eventually, as they return to normal, it's no longer associated. So that's a kind of question TVEM can be used to address. Also, if you are randomizing people to different smoking cessation interventions, and then they're asked to quit smoking on a target quit date, then we might be interested in how the process I just described above, the time varying effect of negative affect and craving, and how that unfolds during a smoking quit attempt, that might look better for people getting the bupropion medication compared to those who are only getting counseling, for example. And the effect of the intervention may also unfold with time. So we'll take a closer look at that exact example in a little while. So first, let's think about a thought exercise. So, sorry. Why is it?
Resetting to that.
I don't know why that keeps changing. Okay, so great. So let's just do a thought exercise for a moment. So suppose an intervention was conducted, a behavioral intervention that was designed to reduce alcohol abuse, and you're going to perform a 2-arm randomized controlled trial, right? So we know how to do this. We conduct a behavioral intervention, and people are randomized to get treatment or to not get treatment. After the treatment is administered, let's say that after the treatment, we have one post-baseline follow-up and see, well, did the intervention work, yes or no? Or maybe we follow them twice after the intervention and we see, did the intervention work at the first time post-baseline? Did that effect still exist at the second time post-baseline? And maybe we actually have many time points measured post-baseline, and we could think about the intervention effect unfolding over time and sort of in the sense of a moving window of time. So let's look at that graphically. So in this graph, oh my gosh, slideshow. Where's the animation? Some trouble here.
Yeah.
Okay, so so in this intervention, let's again, this is a heavy drinking reduction behavioral intervention, and the placebo group at time 1 after baseline. So after the post-test assessment, the placebo group has a rate of heavy episodic drinking in adolescents of say 0.45. 45% are engaging in the behavior. And in the intervention group, we observe that only about 25% are engaging in the behavior. And let's say that that is a statistically significant difference. So great, we conclude that our intervention worked, and maybe we take it to scale. Let's suppose we followed them an additional follow-up time point. Now we have time 1 and time 2. And so we have the same data from time 1, where we have about 45% in the placebo group still engaging in binge drinking at time 1 post-baseline. And we see at time 2 that that ekes up a little bit to about 47% engaging in heavy episodic drinking. And in the intervention group, we see that there's the intervention effect at time 1, as we had observed, and we see that the intervention effect weakens slightly by time 2. So now we have a full 35% in the intervention group engaging in the behavior. And so the difference is smaller, and it may or may not be still significant at time 2. Okay, so this is a time-varying intervention effect. Now let's suppose that we actually observed individuals, adolescents, at 10 time points after the intervention. Maybe we checked in with them every month in the year after the intervention was conducted. And we see the same data at times 1 and 2. And then if we track it over time, we follow it up at time 3, 4, 5, 6, 7, 8, and we see that the intervention effect weakens and weakens until there's no effect at all between the intervention and the placebo groups. But perhaps around time 8 is when they're graduating from high school, say, and then they're heading into the summer. And lo and behold, we see that there's an intervention effect at time 9 and at time 10, so it reemerges as a significant effect. So maybe there's this delayed effect of the intervention when the adolescent's context changed. And if we had not looked for a time-varying intervention effect, we would never understand the process of the intervention effect unfolding over time. So as I said, we see the same data at times 1 and 2. The intervention effects seem to go away, and then it re-emerged after, in this case, a transition out of high school. Okay, so let's talk a little bit more about the time-varying effect model. So in a nutshell, TVEM is a direct extension of regression. All of you, I am certain, have used multiple regression analysis many times in your careers. And if you understand linear regression, you understand TVEM, and you will within the next 15 minutes. You'll know just what it is. It's a really natural and intuitive extension of linear regression. Okay, so the work for developing TVEM was funded by our P50 Center grant from the National Institute on Drug Abuse. And so first of all, why do we collect longitudinal data at all? Well, if you ask any behavioral scientist, likely they will say that we want to capture and quantify temporal changes in some sort of outcome and potentially changes in time-varying covariates. Okay, great. I'm a big fan of longitudinal data. It's how we want to study the emergence of behavior problems. But also, I would argue it may be very natural for us to expect that not only do the outcomes and the covariates change over time, but the associations between covariates and outcomes may change over time. The associations may change over time. And in regression, we're talking about regression coefficients, right? Slopes. So the time-varying effect model is designed specifically to evaluate whether and how associations between variables change over time. So let's look at it mathematically really quickly here. So regression coefficients, as we know from linear regression, express the associations between variables, between the x's and the y. So a traditional bivariate regression predicting our outcome y from our covariate x looks like this, where we have y expressed as a function of an intercept and a slope that's associated with x and an error term. So we fit this with the goal of interpreting and hypothesis test for the significance of beta 1. So how do we interpret beta 1 in linear regression? Okay, this is a great quiz for my regression class students, right? The slope is interpreted as the expected change on y corresponding to a 1 unit change on x, right? And so it's a single number summary of the association between x and y in our sample. It's a single number summary. TVEM takes those coefficients in regression and allows them to be dynamic. So I'm showing you the regression equation now for TVEM. So we're starting again with bivariate regression. The association between x and y is what is of interest. But if we believe that that association, that beta 1, is dynamic and changes over time, then we can express in TVEM parameter estimates to be estimated as a non-parametric continuous function of time. So I'll show this to you in a little bit more concrete way next. So this blue curve on the figure shows a hypothetical regression coefficient that is estimated in TVEM. And again, it's a non-parametric continuous function of time. Does this mean that we have time continuously measured? No, we don't. In real life, we never can assess individuals in streaming real time unless they're wearing some sort of wearable device for passive data capture. But I'm talking about survey data. Maybe it's intensive longitudinal data, or maybe some individuals in this study were assessed at times 1, 6, and 14, and others were assessed at times 6, 13, and 19. So, but we have coverage across that time. And the most important thing is that our research question embodies an interest in the association changing with time. So TVEM estimates regression coefficients as flexible functions of continuous time, and I'm talking about the intercept changing as a continuous function of time, and also the slopes or the associations between x's and y. Okay, and so remember how in linear regression I said that the slope for the effect of x on y was a single number summary? In TVEM, I'm showing you here a sample regression coefficient function. So we no longer estimate regression coefficients, we estimate regression coefficient functions. And so instead of putting an estimate for beta 1 in our tables that we love to do in our manuscripts, instead we are publishing lots and lots of figures. And this figure represents one parameter coefficient in the model. It just happens to be varying with time. And so you see time is on the x-axis, however time is coded in your data, and the regression coefficient is in the y-axis. Okay, let's step back for a minute. I just want to catch all of you up to speed. You're hearing today about time-varying effect modeling. It's a really new procedure. It is starting to be used more and more. It's taking off very rapidly. But I want to give you a sense of sort of the history here, since we're able to capture it. We're so early in the process. So in the 1990s, there was a technique called functional regression analysis that was introduced in the statistical literature. And it never made its way into the literature that behavioral scientists read. But a lot of the fundamental work in this area of TVEM was done in the 1990s by statisticians. It wasn't until 2010 when the Methodology Center released its first SAS macro for estimating time-varying effect models under the direction of our esteemed colleague Renzi Lee. And you'll see a picture to the right on your slide of the Methodology Center's software download page for TVEM. So it's you can get there from methodology.psu.edu. If you want to check it out, then you can click on free software and you'll see the page for TVEM. And our software is free to download. If you're a SAS user, it's very, very simple to use. So this was the first time that TVEM was become available to behavioral scientists. Now, in the early years, in the early 2010s, we were motivated to use TVEM to analyze intensive longitudinal data. So in 2012, we started to put the word out there for how TVEM could be used to estimate regression coefficients as they unfold across intensive time using data from ecological momentary assessments. And so we began to really work in this area, primarily in the area of smoking cessation, nicotine, and tobacco research. And then in 2013, we began to push this direction a little bit further, and we started to introduce TVEM for other applications as well. And it turns out, our belief is that TVEM has very, very broad applicability to all of our behavioral and health research that goes far beyond the analysis of ecological momentary assessments. And we published a supplemental issue of nicotine and tobacco research that was focused on EMA methods. And this was the first year we started to see uptake of TVEM by other behavioral and health researchers. So this was an exciting time for TVEM. And then we offered our first Summer Institute on Innovative Methods on this topic in 2015. And so the software continues to evolve. We added random effects. We're working hard on getting ready to release a version of TVEM that includes complex survey weights. And so the software development continues, as do the application areas that we see for TVEM. So let me walk through two applications with you. The first is talking about smoking cessation recovery as a dynamic process. So this is a study of nicotine addiction and recovery from it. We know that tobacco use is the leading cause of preventable death globally. And this is important. You know, people try to quit all the time. 95% of cessation attempts end in relapse, with withdrawal symptoms being listed as the primary reason. So we argued that an improved understanding of withdrawal symptoms and how treatments can alleviate them, and of course, as you can imagine, I'm thinking about the dynamic process of withdrawal, might lead to new treatments or inform tailored treatments, and treatments that could be tailored to individuals with certain characteristics, as well as tailored to certain times in their quit attempt. So the overall goal of this particular application was to apply innovative methods to existing data from a randomized controlled trial on smoking cessation to gain knowledge that could inform the next generation of more nimble and adapted, tailored smoking interventions. So this is the broad goal of the project. So let me tell you about the data that we were analyzing, and just for the record too, NIH is very interested in funding secondary data analysis grants. That's how we funded this part of the project. So, so it's a great way to think about answering new questions in your research using TVEM to try to get that funded by NIH. So this is data from the Wisconsin Smokers Health Study, and they call it WISHES. And this is a very wonderful data set that was collected by our colleagues at the University of Wisconsin, Megan Piper, Tim Baker, and Mike Fiore. And so they had a very large sample, 1,504 daily smokers enrolled in a cessation trial. There was a randomized trial funded by the National Cancer Institute. And so for the purposes of today, I want to talk about two groups. There were 6 treatment groups, but that we're going to just talk about 2 groups, placebo-only group and the treatment group, which had some combination of bupropion medication, the nicotine lozenge, and the nicotine patch. And importantly, in this study, they did real-time assessments of the dynamic phenomena of interest, the withdrawal symptoms, mood, behavior, context, smoking bans, anything that might be relevant to their momentary risk of smoking lapse were assessed in real-time assessments on a mobile device. So here's a depiction of the study design. So after the orientation session, they started a three-week countdown to the target quit day. And at 2 weeks prior to their target quit day, their planned quit day, they received their wearable device, their mobile device, and started to provide EMA, ecological momentary assessments on their device 4 times per day. And they continued that through the target quit date and through 2 weeks after the target quit date. And so you could imagine the very interesting dynamic processes that might be leading up to a very stressful quit day and coming out of the quit day through the recovery of withdrawal. And then they also collected and followed up people for up to 26 weeks, and I think even beyond that. And the EMA that we're going to be analyzing here, I said they were assessed 4 occasions per day. As soon as they woke up, they initiated a survey. They were surveyed at 2 random times during the day. They were beeped so that they were sampled randomly in time, in space, in their natural lives, and then at bedtime. And this was done every day for several weeks. So the specific goals of this study were, first, to study the underlying dynamics of craving during a smoking cessation attempt, and 2, to estimate the effect of an intervention on not just reducing craving, but the effect of the intervention on decoupling craving from its key drivers, for example, negative affect. Okay, and details appear in the published article from 2014. So the measures in our study, something you'll see in both of these studies is that the variable list for both of these studies is quite short. The data sets are very small, but the results are quite nuanced. So the variables in this study, there were 4 of them. The outcome, which is your craving to smoke, and this was captured during the first 2 weeks after quitting smoking. And it was intensively assessed, so for 14 days, 4 times per day. We had 2 predictors. One of them was baseline nicotine dependence. So this is a static characteristic of the individuals at time of randomization to treatment. Their level of nicotine dependence before they quit was assessed. So again, the predictor is not time varying, but its effect certainly can be time varying, and we'll see an example of that in a moment. The other predictor was in fact time varying, and it was their momentary mood, their negative affect specifically. Okay, and then we had a moderator that was the placebo versus the intervention group. So we had 4 variables. Next, we specified our TVEM, our time varying effect model. And so we had to think about, within each intervention group, what do we really think varies with time? We have to specify this as scientists, right? So first of all, of course, we think that our mean craving over the 2-week period after quitting changes with time. So that's our intercept. So we are not going to estimate an intercept. We're going to estimate an intercept function as a function of time. Second, negative affect itself is changing with time, and we would like the effect of negative affect to be changing with time. So we're going to estimate a slope function or a coefficient function for the effect of negative affect on craving. And finally, we have baseline dependence, but we want the effect of baseline dependence to be allowed to unfold with time during the quit attempt. So a second slope function. Okay, so that's how we would think about specifying our model. Then we have to actually understand what TVEM is estimating. And so the equation looks something like this. We have craving for individual I at time t is expressed as a function of an intercept that varies flexibly with time, plus slope as an effect for negative affect for individual I at time t. And again, that slope is allowed to vary flexibly with time. And finally, we have an effect of baseline dependence, DEP for dependence. For individual I, it's static across time, but the slope is allowed to unfold flexibly with time. And we have our error term. So if you're used to looking at multi-level models, this is going to look quite similar for repeated measures, but it's not the same thing. And we are actually here estimating linear regression where the coefficients are non-parametric functions of time. So here's one of the results. This is the effect of negative affect, our momentary negative affect on craving. And you will see that, so the placebo group, coefficient function for the placebo group is in red, and the coefficient function for the treatment group is in blue. So let's just orient ourselves to this figure. So these are regression coefficients. On the x-axis, we have the number of days since quit date. So it goes from 0 to 14. And on the y-axis, we have the effect of negative affect. So negative affect and craving were continuous variables. So these are regression coefficients and betas. And so we can interpret them. So let's try to interpret them. So for the placebo group, on day 0, at the very beginning, or right after they quit, the association between negative affect and craving is significantly different from 0. And in fact, the coefficient is almost 2.0. So for every 1 unit higher on negative affect, they are expected to be nearly 2 units higher on craving. In contrast, for those in one of the treatment groups, they're grouped together here, the association between negative affect and craving right after they quit smoking, so at day 0, that association is much smaller. It's about 1.3. And you'll see by the non-overlapping confidence intervals that the effect of negative affect on craving was significantly stronger in the placebo group for a day or 2, and then they were the same. So if we didn't think about the difference between placebo and treatment effect varying with time, then we would have never found, excuse me, we would have never seen this time varying effect. Excuse me. Here's one more finding. So this is for baseline dependence. Remember, baseline dependence is a single number that everyone has at the beginning of the study. And we expect that the effect of baseline dependence on craving may be pretty static. And in fact, for the treatment group, those receiving some sort of treatment and pharmaceutical or nicotine replacement treatment, the association is significantly different from 0. So the higher your dependence level at baseline, the higher your craving. And that relationship is very, very steady throughout the 2-week period. But what we see is in the placebo group, those not receiving treatments, after the first week, we see an elevation in this association. So the placebo group, actually, their baseline dependence is very intermingled with their craving, their momentary craving, after that first week of burn-in time, and they're still abstinent. They're struggling more. They're likely struggling more if they have higher baseline dependence and they are in the placebo group. So implications we drew from this first study. One thing that I like to focus on is I think that TVEM, this shows how we can use TVEM to think differently about intervention effects. So with time, intervention can change relationships between variables. It doesn't just reduce the outcome, but it might change key relationships over time. And in this case, we see that the intervention diffused the role of negative affect, a key driver of craving, very early in the quit attempt. And it was only active, and it was only an active effect for about 2 days. But those 2 days could be crucial for individuals to get over the hump in their quitting attempt. And broader implications, I think that this shows how we can think about the effects of static variables, baseline variables. It could be race, ethnicity variables, anything that doesn't change with time. But the effects can evolve over time. And I think this is very much the case for genetic variables, and gene expression can change over time and age. Also, the effect of a treatment in a standard RCT can be time varying as well. So we don't just say, does the treatment work, yes or no? We say, when does it work? And it allows us to model a potential intervention process that we might posit. And again, I think that this information could help get us one further step down the road toward tailoring treatments to individuals with certain characteristics and also to time. Okay, great. So let's step back out for a minute. That was an example of how TVEM can shed light on dynamic processes, in this case, modeled with data that were intensively assessed within individuals. Now we're going to step back and look at e-cigarette use in adolescents today and take a very developmental perspective. And I say that with a smile on my face because we're going to be using cross-sectional data. But it's very much a developmental process that's under study here. So this work was funded by an R01 awarded by NIDA to analyze existing national data to advance our knowledge of substance use and its correlates from, again, the etiology or a developmental perspective. Okay, so why e-cigarettes? Well, these slides are about a year old, and so they're already badly out of date as the e-cigarette literature emerges very rapidly. E-cigarettes were developed originally as a reduced harm product, so they were considered a safe alternative to traditional cigarettes. That was the assumption, that was their goal. These are inhalation activated devices, and so when you inhale, there's a heat produced which turns a solution into vapor. What is in the solution is questionable. The more I learn about it, the more I learn it's typically not nicotine, but the idea was that these devices were meant to be used for nicotine and possibly with other flavors. And there are, of course, other toxins in there as well. The good news is that e-cigarettes eliminate the combustion or the smoke. However, their long-term health effects are still to be determined, and the more that they're studied, the more I think they are highly problematic particularly for youth. But the rate is rising very rapidly. E-cigarettes are used significantly more commonly than traditional cigarettes by today's adolescents. Until last August, they lacked FDA regulations. And a question that we have been wondering is whether e-cigarettes might actually be a gateway to traditional cigarettes. Maybe kids are using e-cigarettes that have nicotine in them, and then they're getting hooked on nicotine, and then they're going to be driven to smoke the carcinogen-laden traditional cigarettes. So we wanted to examine this a little bit. So this study uses data from the National Youth Tobacco Study. It's a very straightforward and useful cross-sectional data set. These were data from 2014. This was commissioned by the Center for Disease Control and Prevention to assess tobacco-related beliefs, attitudes, behaviors, and exposures to campaigns and other influences by adolescents today. And so it's also a very large sample. We had 22,007 U.S. middle and high school students, so a very large sample. And the students in this sample spanned ages 11 to 19. Okay, so that it gives you a flavor, a window into our thinking right now. We were interested in looking at correlates of e-cigarette use across ages 11 to 19 with cross-sectional data. And it was nationally representative data, so it matched population characteristics pretty well. So the goals of this specific study were to understand a little bit more about the etiology of traditional and e-cigarette use and co-use. So first, we wanted to estimate disparities in the rates of use across adolescents. And when I say disparities, I mean sex differences and racial ethnic differences in the rates of use of the two products. And, excuse me, and we would use TVEM for that. And then importantly, in goal 2, we wanted to estimate the rate of use of both products as a function of age. And so maybe some students only use e-cigarettes, some only use combustible, some use both. So we wanted to estimate the rate of their individuals using both. And so these results are unpacked in a recent manuscript that's in Press at Addictive Behaviors, which we would be very happy to share with anyone online today. Okay, again, we see our measures section. Again, we have a very short list of variables, and this is cross-sectional data, so it really couldn't be simpler in the measures department here. We have a binary measure for current traditional cigarette smoking. Yes, no. 6.4% were currently using traditional cigarettes. We had a single binary variable for current e-cigarette smoking. Yes, no. 9.2% were reporting e-cigarette smoking currently. Okay, importantly, we had age in our data set. Well, in this data set, we have age to the nearest year. This age variable is our time metric in this analysis. It's that we're interested in looking at rates and associations across age, across time, across age. So, so for the age variable, you always want to retain a measure of age in this case, or whatever your time variable is, with the greatest precision possible. So when we analyze the AdHealth data and look at developmental change, the AdHealth assessed age to the nearest month. And so we will keep the age to the nearest month in there, and we will code that to the decimal place. But here it was just to the nearest year, which was fine. We had a binary variable for sex and a 3-level variable for coding racial ethnic group. Okay, so again, we've got our data set, we've got our research questions. Now we have to specify our model. Here we're going to be looking at rates of a behavior. So we're going to use logistic TVEM, right? So just think about your logistic regression analysis and add the time varying element to your coefficients, and you've got logistic TVEM. So what varies across age in our study? Well, we believe the probability of cigarette use will vary, and the probability of e-cigarette use will vary. So in 2 separate models, predicting each of those outcomes, we would specify age-varying intercept values. Obviously, sex and race ethnicity are unlikely to change across age, and in fact, this is cross-sectional data, so they absolutely could not. But their effects could be age-varying. And then finally, we are very interested in the intersection of use of the 2 types of cigarettes within individuals. So are adolescents who are using one type of cigarette at advanced risk of using the other one? If so, by how much? And at what age? So that association between cigarette use and e-cigarette use, they're both binary variables. So we're talking about an odds ratio. That odds ratio is specified to be age varying. So here is one of the models that we fit. So you'll see the logit, the log odds of cigarette use, is expressed as a function of an intercept, which is age varying, because we posit that the probability of cigarette use varies with age, plus the effect of sex on the log odds of cigarette use. And we believe that the effect of sex, the sex differences, or the rate of use across sex groups might vary with age. So we specify both coefficients to vary with age. Here's another example of predicting e-cigarette use from traditional cigarette use. So let's take a peek at the results. So this depicts the sex differences in e-cigarette on the left and traditional cigarette use on the right across ages 11 to 19. And so males are using at higher rates, they're depicted in the blue lines, and females are using at lower rates in mid-adolescence, and they're depicted in red. And so with TVEM, you'll see these are prevalences, and there's a point estimate that is a function over time. That's the solid lines. And there are, for any age, you can look vertically above that age period, say e-cigarette use at age 15. You can look vertically and see, okay, the males, about 15% are expected to use e-cigarettes. And vertically, you see the 95% confidence intervals at that age. So we have age-specific confidence intervals here too. Females at age 15, about 10% were expected to use e-cigarettes at that age. And so what do we see here? What do we want to really think about interpreting here? Well, there were no significant differences in the rate of e-cigarette or traditional cigarette use across sex until age 14 or 15. But between ages 15 and 18, males were using at higher rates. And then around 18 to 19, where we had a little less data, remember these were high school kids, the association was no longer significant. Interestingly, we also interpreted racial ethnic differences in the rates of use across ages 11 to 19. The first look at the right panel, traditional cigarette use, and we see in red the rate across age for Black, middle, and high school students. And in blue, we see the rate for white. So as with many, many prior studies, we see confirmation that whites are using at higher rates than Blacks. And in particular, this is significant between ages around 14 to 18 and a half. Hispanic, what you see around ages 15 to 18, Hispanics are smoking traditional cigarettes at a rate that's right in the middle between Blacks and whites. That's also what we've seen in many, many prior studies. But let's now focus in on the age range of 11 to 13 for traditional cigarettes, and you see that Hispanics are actually smoking traditional cigarettes today. Hispanics aged 11 to 13 are using at even higher rates than whites. So this is historically a very recent trend, and you see it in e-cigarette use as well. Between, let's see, the green and the blue curves don't overlap between around 11 and a half to 14. So middle school Hispanic youth are using e-cigarettes and traditional cigarettes at higher rates than whites and certainly Blacks. Okay, and finally, what is the association between using one product and using the other product? So we are showing here, again, on the x-axis, we have age 11 and 19. And on the y-axis, these are odds ratios, and that is an odds ratio of 45. How do we interpret this? So these are age-specific odds ratios. So let's take age 12 as an example for interpretation purposes. So among those age 12, adolescents using e-cigarettes are at greater than 40 times odds of using traditional cigarettes compared to 12-year-olds not using e-cigarettes. So you can get a sense from this plot about the co-occurrence of using both products as a function of age. So some implications we drew from this second study I think are relevant maybe for policy and prevention. The identification of key ages of risk. We were able to identify them using TVEM, and those could inform targeted age-appropriate interventions. We find that traditional and e-cigarette use really does go hand in hand, particularly in very early adolescence. And then I think importantly, this early use of e-cigarettes and also to combustible cigarettes was significantly more likely among Hispanic youth, only during middle school, but suggesting a greater risk, I believe, for future nicotine dependence and future health disparities between Hispanic and white and Black individuals. Okay, so let's just have just a few concluding remarks. Next steps, future directions. You know, one of the things that we in the Methodology Center spend a lot of time thinking about and working on is how to draw new information from complex, contemporary data sources. And, you know, intensive longitudinal data is one of those areas of big focus for us. And ILD, intensive longitudinal data, this, you know, can come from ecological momentary assessments where you're actually surveying individuals intensively, or it could come through some sort of wearable device that is gathering data more passively. In either scenario, you know, these data are complex, and sometimes we have data coming in at different rates of intensity over time, and it can be very complicated to figure out how to get scientific information from the data. There are other types of complex data sources today, electronic medical records, genetic data, and we can't forget social media data. But big data and complex data are places of high opportunity, not just opportunity for scientific productivity and grants, but opportunity for knowledge, gaining new knowledge. And I think that there's many health areas that are stand well poised to move quickly in this direction. I believe TVEM specifically can be used to unlock new knowledge from existing data sources. You know, we can use TVEM to understand complex processes that unfold with time in many ways that we can't even yet theorize about because our behavioral theories are not that advanced and specific. We can use TVEM to estimate the dynamic effects of interventions so that we know a little bit better about when they work for whom. TVEM can tell us about developmental processes and associations over time, maybe revisiting the rich literature on adolescent risk factors for substance use and placing them into context of developmental age more specifically. And I believe TVEM has a lot of promise for understanding associations and how they unfold across historical time. And we have used data from Monitoring the Future to do just that. We've used data from 1976 until today to look at how perceived risk of smoking and actual rates of smoking have evolved over historical time, maybe having policy implications. And I think the complex link between the age of onset of a behavior or a phenomenon can be studied with respect to health outcomes and problem behaviors and so on. So we've done a little bit of work linking behaviors and looking at them as a continuous function of not time and not age, but actually across age of onset. So there's a lot of new questions that could be unpacked with TVEM. I would like to give a shout out to my close collaborators in the Methodology Center, John Ziak, Renzi Lee, Michael Russell, and Sarah Vasilenko are 4 of the collaborators I've been working most closely with over the years, and that is Renzi Lee, the original statistical developer of TVEM. So I think our field is indebted to him. And I would really like to thank the National Institutes of Health for all of their generous funding of innovative methodological research that we really do try to use to advance public health. So with that, if you are still with us, I am grateful for your attention, and I want to thank you very much. I would love to stay for an hour and take questions. So I will be here. I will probably sit down in front of the computer so we can have a face-to-face conversation. And we'll open it up for questions.
Yeah, so this is Bethany again.
Yeah, that's great.
So you sit here. Hello, everybody can see Stephanie now, right there. Wave.
Hello.
Hi. We're gonna make her big in a second, and Erin, our moderator here over in this window, is gonna ask your questions. Please feel free to keep those questions coming via the chat, and we'll try to keep up as much as we can. And please don't forget to leave your feedback. If you have to go, we understand. If you really like this session, please let us know, and feel free to suggest topics. We can't promise anything, but we will try.
We've lost almost no one.
Okay, great. So people are still on, so I'm guessing you all have questions. I won't know all the answers, so I will tell you when I don't know. This is a really active area of methodological work and also application to types of data. And it's a little bit like the Wild West out there, but we're having a blast, and a lot of people are getting involved with using TVEM. So, Erin, do you have any questions to start us off?
Yeah, we have a good set of questions that have come in. There probably is time for more than we have right now, so
Okay.
if people submit them, we can still try. I'll start with the one question that was asked twice, which was, is there a way to do TVEM in R?
Well, that's a great question. That is a question that my colleague John Ziak, who was on the slide at the end, could answer definitively for the group, and maybe we could add that to an FAQ. There is a package in R for for doing functional data analysis. And so I believe some of the functionality does exist in R today. It was not developed by our team or documented by our team. But if you really understand the model you want to specify, I think it would be possible to do much of it in R. So we developed syntax. I wonder if I have that slide here. We developed syntax as SAS macros, and if I'm able to return to my slides, I bet I can. But
Your slides are actually still up.
active, yeah.
Yeah.
I might have a sample syntax to show you. I can certainly pull it up. And the sample syntax is extremely simple in SAS. But yeah, so the question was about R, and there's an R package that does some varying coefficient models.
Yes, that's right.
So, but I can't speak to the features of it specifically.
So we're just gonna pause for 1 second.
Mm-hmm.
So we do not have you currently large on the video.
Okay.
Do you want to keep your slides up in case people ask questions?
Yeah.
Can you all comment in the chat box? Is this working okay? Stephanie's a small figure. Is that all right for everybody?
All right, great.
Yeah, we're just gonna keep doing what we're doing.
That's great. You don't
Thank
need
you.
to see me bigger than that. Okay, another question.
Yeah, okay. So I'll try and go through them basically in the order that they came in, just in the sense of some sort of fairness. Yeah, exactly. Okay, so a question about covariates. In the first example you used, there were very few. I am used to working with many. Does this first example use a few predictors just to simplify the example, or is there a larger reason? Thank you.
Yes, the answer is yes. It's using it to simplify the presentation and the example. And you'll see that most of the early papers we've published with TVEM to date, and again, you know, they only started coming out in 2012. So most of the early papers also do not have a lot of covariates in the model. And it's really because it's challenging to convey what you're doing in one paper when people are not yet familiar with TVEM. So if you're going to start using it in your research, you need to be, you know, really thoughtful about how much you have to explain what the model is doing and how much you have to focus on interpreting the figures for people who are not familiar with TVEM. So small is good, simple is good in that respect. Having said that, remember that at any particular age, so think about a vertical slice in the plots at one particular age or time, you are fitting nothing more fancy than multivariate regression. And so you could think about having blocks of control variables, interaction terms. We do interactions a lot. Any kind of variable you would have in there as a predictor of your outcome. In multivariate regression, you may have in TVEM. And then the interpretations would follow. So you would estimate a slope coefficient for the effect of, say, height on weight. And for people age 18, you would say for every 1 unit higher in height, you are 7 pounds larger in weight. And if you had control variables, you would say controlling for X, Y, and Z, or holding X, Y, and Z constant. If you had an interaction term, say height multiplied by sex, biological sex, then you would have a TVEM estimating height as a function of, weight as a function of height, sex, and height by weight. And you can interpret at what ages height and weight are significantly moderating, height and sex are significantly moderating each other's effect on the outcome. And so some of our work right now is to really focus on conveying how TVEM can do non-parametric or time or age varying moderation. So sex moderates an association. When? For whom?
Great, thank you very much.
Mm-hmm.
So we also had a pair of questions about multi-level modeling, and I'll ask them together.
Okay.
The first one just didn't quite grasp the similarities and differences as you were explaining, and the second one was in terms of similarity to multi-level modeling, how similar would it be if we were, in the context of MLM, to interact time with negative affect when predicting craving?
Right. Okay. I'm going to answer the second one first, I think. So I'll try to do this with my poor memory. So if we put in, so in our first example, time is the x-axis. We could have alternatively looked at the association between negative affect and craving, and we could have put in as our covariates negative affect, time, and negative affect times time. Okay, so that would be as close as you could get to fitting TVEM in a multi-level model. And in that case, you'd also have to accommodate the multi-level structure of the data with random effects or a GEE approach. So you still have to take into account the nesting, of course, within of repeated measures within individuals. So what would this give you? This would give you an overall estimate, marginalized, the overall estimate of the association between negative affect and craving. And it would give you, so no intercept function, but you get one marginalized association between negative affect and craving. And you would get a main effect of time, which would tell you whether how craving might change linearly across the 2-week window. And then a test for whether the association between negative affect and craving changed linearly with time as well. So you are imposing your linearity assumptions within time in your regression prediction, and importantly, I think, over time as well. So you are pre-assuming that the developmental change, the developmental course of craving during a quit attempt is a straight line, and that the association is changing in a linear way as well. And so I think that, if you're looking at a small time window, or you have everyone in your sample was only assessed at months 1, 3, 5, 7, and 9, and those are your times, I think you can really do quite a lot with multi-level modeling. I use MLM a lot, but if you have theoretical reasons or very nuanced data that would allow you to dig deeper into time unfolding, processes unfolding with time, TVEM is a wonderful exploratory approach for that. One could even use TVEM to first see if the associations are varying flexibly with time. And then if you really wanted to, you could, especially if they were fairly linear, then you could switch back over to multi-level modeling and write it up that way. But you wouldn't know until you look. It's kind of like an interaction term. We don't know if an interaction is significant until we estimate it and look. Okay, so the other question I think was very related is multi-level modeling, how it's different. I think I covered that, but feel free to write in follow-up questions.
Yeah, I think you covered it too. But again, if I'm incorrect, please hit us with another chat. Question about the time metric used in the nicotine addiction study. Mm-hmm. Since there were 4 assessment points per day, person wanted to know if it was measured in hours and then presented in terms of days.
Oh, great. So it was measured in seconds. It was truly real time. And so the mobile device, it's a little bit dated. They were using Palm Pilot. And the device is actually time-stamped every assessment at every point every day. And we kept time to the nearest second, or even maybe greater detail. But for presentation purposes, it was estimated as a continuous function of time. Our data were almost continuous in time. But I was simply labeling the x-axis with anchor points so that we could follow along and really make sense of what was unfolding when in that 2-week window. Great question.
And then there was a follow-up to that, which I thought fit in. if there is a different N at different time points, because some people wake up at 9 a.m. and other people wake up at 6 a.m., is there a lower limit in terms of how many or how few participants are needed for getting appropriate estimates?
Yes. Oh, great question. So I think power analysis for TVEM is not well established yet in general. And I think, but more fundamentally, sort of, when we think about estimating a TVEM, we need data support at all general points in that time axis. We need the support of data to estimate a coefficient at that particular time. Okay, that said, there's no easy way to answer how many data points you need at a particular time and so on. And again, if it's continuous time, then no one will have assessments at the exact same time necessarily, you know, if it's randomly but continuously in time. But there are a couple of things that we can fall back on and rely on. One is if we have an age period or a time period where for some reason we didn't have a lot of data to support it in that particular period, what you'll see is your associations can still be estimated and the confidence intervals will appropriately get larger where there's less data to support the estimate. So our confidence intervals are point-wise confidence intervals that reflect the confidence that we have at that time or age. And part of that determination is based on the sample size that you have at that age, roughly in that age range, on which to inform the estimate. So your confidence intervals will alert you to that. I think and something else we can rely on too is an understanding, and it could be a general understanding at first, but TVEM relies on a spline estimation. And what that basically means is that there are smoothers being applied in the background to these coefficient functions. And so the estimate at one particular moment is actually borrowing information from nearby moments to triangulate on the best estimate at that particular time or age. And so if you actually are missing data at one age completely, but you have data in surrounding ages, it's not a problem. You can still estimate it, and the spline regression will handle that for you. I will say, you know, if you have a longitudinal panel study like AdHealth, and maybe there is selective dropout, if the people present in the study at age 12 are fundamentally different in important ways from the people who are still in the study at age 32, then that's something that you need to think about. Maybe you want to do case-wise deletion and then weight the data up to the national estimates. That would be a good way to go. Or maybe you just want to do you know, a description of who's dropping out of the study, and so that the results can be taken into context.
Thank you. Now we'll get to the advanced questions.
Oh boy, seriously, this is already hard.
People are loving it. You're doing great. In TVEM publications that examine moderation, the authors usually estimate separate models, for example, for treatment and control groups, which has the effect of interacting the group with all other variables in the model. If I wanted to examine moderation with selected variables rather than all variables in the model, and include a multiplicative interaction term in the full sample model, could you provide some guidance on how to interpret the test of that interaction as shown in the graph for that multiplicative interaction term? Thanks.
Okay, so I'm a big fan of moderation analysis in TVEM, so this is a great question. I think TVEM is an outstanding way to look at moderation. You are correct that most of the previous studies, published studies that have looked at moderation, like full moderation, for example, treatment versus control, particularly our earlier papers, we would separate the data into two separate data sets and look at these you know, very nuanced dynamic processes and model them for treatment group and model them for control group. And sometimes we would plot them together. So there are pros and cons to this approach versus a full sample moderation analysis. One pro is that it's much easier to digest the information and to produce plots that allow a parallel comparison of the two groups. And so that is, so those are the kinds of results that I showed you today for the treatment and placebo smoking cessation study. So that was, it's easier and it's straightforward and interpretable. And in fact, in many times, that's where I still start today. I will separate the data, understand the processes in the two groups. There's no reason why you have to do that, though. Again, you've put the full data set together, and I actually more and more have been leaning toward doing this process where you put it all in the model together, and you estimate the effect of X, the effect of the moderator, and the effect of X times the moderator. And you can have that for many coefficients in the model. A moderator could moderate 3 coefficients of X, and that's fine. So again, anything you could express at a particular time point as a moderation question, you can express in TVEM as a time-varying dynamic moderation question. It's so awesome, the kinds of questions we can now address. And so you would have, in the results, if you fit a TVEM like that, the challenge, as with any regression analysis with interactions, the challenge is on interpreting those interactions. So we're actually writing a book on the basics of TVEM right now, and that's one of the big things that I want to cover so that it's more straightforward for people to get their head around. So one of the first things you see, if you fit a model, a TVEM model with moderation of, say, sex differences in the association between mood and craving over age, you'll get a coefficient function for the effect of mood. You'll get the main effect of mood. You'll get a coefficient function for the main effect of sex. And you'll get a coefficient function for the interaction term. And so that interaction term coefficient function may be significantly different from 0 at certain ages and not at others. And so now you're getting a very nuanced test, hypothesis test of age-varying moderation. And so the coefficient function for the interaction term is very important to interpret in terms of periods, age ranges, or time ranges of significance. So when does moderation occur? When doesn't it occur? So that's super helpful. Then at that point, the burden becomes, how do I plot this and convey it in figures so that my reviewers are going to accept it, and that's the challenge. And so interpreting interactions is always challenging, but plotting the results is the answer usually.
Okay. Thank you. Can TVEM be used in cases where the treatment or explanatory variable is time varying? For example, when looking at workforce status over time, an individual may go from working to unemployed and back to working. Thanks.
Yes, great question. Also, yes, my colleague Rebecca Evans-Pulse recently had a paper accepted at ACER, Alcoholism Journal, that was, the goal was to examine the effect of being in college versus not being in college on heavy episodic drinking as a function of age throughout young adulthood, late adolescence and early adulthood. And so what we wanted to be true to in that model, this is an example of how you can do this. What we wanted to be true to in that model is the fact that individuals between ages, say, 18 and 30, anyone in that age range may be in college at the time, enrolled in college. So we understand college being a risk setting for frequent binge drinking. Well, that's true, but it's probably not true at all ages. It's probably true at the normative ages of 18 to 22 or 23. But what if someone's in college at age 25, 27? And so the predictor in that model was college enrollment, and it was time varying. People could go in and out of college. In this case, it was cross-sectional data, so at whatever age people were, they either were in college or they weren't. But if it was longitudinal data, they could go in and out of that status. And we can still estimate the age varying or time varying effect of that time varying covariate. So absolutely, time varying covariates have a big place in TVEM.
Just for everyone's information, just to take a second. If you see Stephanie or I staring off the side of the screen, it is because we are literally right beside one another.
Aaron's right there.
I didn't think that was clear, so anyhow. So the next question is just, is it possible to assess interactions of predictors or moderators? For the e-cigarette study, for example, is it possible to get estimates for the interactions between sex and race?
Oh, sure. So yes. So you would have to have that research question and then think about, when you're getting ready for model specification, how you want to specify it. So you might have a main effect of sex, a main effect of race, ethnicity, which might be a series of dummy coded variables, and their interactions. And then once you figure out that part of it, you have to decide which of all of those you want to look at as age varying coefficients. And so you could absolutely predict e-cigarette use from sex as a dummy variable, race, ethnicity with 2 or 3 dummy indicators, and then all of their interaction terms, and all of those can be age varying effects. And again, the burden then becomes, how do you present those results? But I think, as an analyst myself, I think that model is the same thing as separating the data and running it by group to get the results. It's essentially the same thing. It's not exactly the same thing, but it gives the analyst an opportunity to look at the effect of race, ethnicity for males, and then look at the race, ethnicity effect for females. You can eyeball it, see where the action is. You can go back to the full model where you have it all interacted. You can test, very nuanced. You can test age-varying interaction terms, and then figure out how you want to present the story. From your full model, you can derive any graphic depiction of your results that you wish. Just like in regression, when you have to unpack an interaction term and produce figures to interpret the associations, the complex associations, you can do exactly the same thing in TVEM. I like to pull my final parameter estimates into an Excel file, and from there I can generate any hypothetical people and mean curves and so on. And so TVEM will dump out a SAS data file with parameter estimates at across the time axis, broken at 100 equal time intervals. And so you can create your publication ready figures right in Excel. And for me, that's the easiest way to do it. Some of my colleagues like to generate the plots right in SAS, but I find that to be a little bit difficult to control.
Thanks. So a longitudinal example question. The gaps between the lines and the confidence intervals between two groups, e.g. sexes or race ethnicities, indicating significant differences, were of varying size across age, starting small and then getting larger. Can we make statistical inferences about the extent of the differences?
Okay, great. So if I understand this question properly, this is a great question. So if we want to look at sex differences in the rate of e-cigarette use across age. So we're going to go back to the first figure I showed in the e-cigarette example. You can estimate the age varying rate for males, and you can estimate the age varying rate for females, and you can plot them together on the same plot, and that's meaningful. So then I was in the talk, and this was a little bit sloppy on my part, but I was roughly interpreting the age periods when the intervals did not overlap as statistically significant sex differences. That's not incorrect, but it's an overly conservative test of sex differences. The proper way to test it and to be less conservative, i.e. you'll find more differences if you do this, is to go back to a full sample model and put sex in as a predictor of the rate of e-cigarette use. And so that doesn't give you the nice output of the rates over age that you can just stick into a figure. But what it does give you is proper hypothesis tests and then we show 95% confidence intervals. So you get age-specific 95% confidence intervals at every point in time or age. And so you could, if you wish, you could produce the 99% confidence intervals or the 90% confidence intervals. You can also, in the data set that's created with your final estimates, you'll get the parameter estimate and the standard error. So, so you could, you should be able to get a p-value for the test of the hypothesis of whether it's significantly different from 0 at that particular age. Yeah, so I think the hypothesis testing of group differences is properly done in a full model where you have it in as a correlate and you evaluate the specific ranges at when, say, sex significantly predicts e-cigarette use. And that is going to correspond to where those curves did not overlap, but it's a little bit more of a statistically higher powered test when you do it in a full sample analysis.
A question about sample size. Is there an ideal sample size?
That's a great question. We don't know yet. So, you know, I think if, you know, again, what you're going to see in TVEM that at time points or age points at which you have less data, your intervals are going to be wider. Right? Just as they would be in a linear regression with a smaller sample size. And so your confidence intervals will be your first clue. With small samples, it's not that you won't be able to run TVEM, it's just that nothing will be significant. So in much the way that it is in linear regression. So by all means, try it with smaller sample sizes. If you have a whole bunch of adolescents and only a handful of young adults and you want to look at age-varying effects, try it. But your intervals will be very tight for adolescents and then they'll get very wide because you just won't have the precision of estimation where the sample size is smaller. So, you know, I don't have any answers. It depends on how complex your research questions are in terms of the model you're specifying at a particular age. How many predictors do you have? How many interactions do you have? Are they binary? Are they continuous? Are they very variable or not variable? So those all factor in. The same factors that play into power analysis for linear regression play into TVEM as well. But in addition, then you have to be thoughtful about, do I have enough data to make inferences at this point and at this point? I'm working on a paper right now that is looking at early marijuana use and the association between being black youth and achieving a college education by age 25. And we're looking at it as a function of age of first marijuana use. And what we see is that if for users below ages 12 to 14, our intervals are so wide we can't say anything about it. But I'm leaving it in the paper because why are the confidence intervals so wildly, outrageously wide at marijuana users less than age 14? It's not that we don't have marijuana users who started between ages 12 and 14. It's that we don't have black college-educated individuals who started using marijuana at age 12, 13, 14. And so, again, it's statistical power. The longer I'm in research, the more I feel as statistical power is so complicated. And so I think your confidence bands will expand as the amount of information you have to answer the questions at that particular age that you have. And so remember, your confidence bands can widen and shrink as you have more or less information on which to base your estimates over time. And that's a good thing, right?
Pardon me.
Yep, okay, I'll take the question. So we have a question about Stata. Do we have TVEM in Stata? The answer today is no. We also develop software for latent class and latent transition analysis as SAS procedures, and we have released those as Stata plugins. But for now, TVEM is a SAS macro, and we don't have an immediate plan to release it in Stata. But I think that we may package our TVEM procedure as an R package for users. We understand exactly how some of the nuances in the data are being handled when we program it ourselves, things like weights, random effects, handling clustering of repeated assessments within individuals. And so we may release an R package, but I don't think Stata is on the plate right now.
And for anyone who uses SAS at all, TVEM really is legitimately not very difficult to run. That doesn't mean it's simple or that it's easy to interpret what you get. But in terms of if you have data, getting results out of TVEM, there's not a steep learning curve for that.
Right. I was going to peek and see if I had a...
there was a question about if you could show kind of... I would like to show you sample syntax in SAS, but go to methodology.psu.edu to the TVEM page. There's a TVEM research area page, and there's also a TVEM software, free software page. And somewhere in there we convey the simplicity of the SAS programming. One thing that I get a question about a lot is oh, you're using AdHealth for a lot of TVEM analyses to study development, but AdHealth only has 4 waves, so how is that possible? And so this slide was meant to convey how individuals could have only 1 or even in this case 4 time points of measurement, and it's nationally representative data. It was a big cohort sequential sample, and it had about 12,000 individuals in the sample followed over time. And but if you look at it in terms of how many data points you have, it's 12,000 by 3.5 or so on average time points per person. We're talking about 35,000 time points, person times, in our data to support this inference of developmental change. And so if you think about the data points, this is actually plotting the points of assessment in AdHealth. And if you know anything about AdHealth, everyone who sees this is surprised that we have such incredibly dense, good coverage across age from a 4-wave panel study. And so this is a great way to think about, could your data support a TVEM analysis if it's cross-sectional or panel data? Well, take a look at all of your person times and figure out, look at a histogram or a box plot or something like this that shows how well you have, what kind of data support you have across the different age periods. Maybe it's only a subset of ages that you have good data for, and so you would restrict your TVEM to just that age range. Yeah, but I don't have sample syntax right here. Okay, yeah, it's historical examples. And age of onset. So this is just a slide showing really briefly how we use TVEM to link the age of onset to an outcome. And then instead of saying, if you start smoking regularly prior to age 14, you're at risk. And if you didn't, you aren't at risk. But thinking about the age of onset in a more nuanced way in the population, what we found is that you see that this is the functional form of the association between the age of onset of
first regular smoking and adult nicotine dependence. And so this age of onset trend gives you much more information, I would argue, about how the age of onset is associated with dependence in adulthood. And we further looked at it separately for females and males, and the pattern is the same, but much stronger for females who start smoking regularly at younger ages. So this is an example of modeling coefficients as a function of age of onset. So some of the time metrics that we've explored, of course, real time, and that was example 1 in today's talk. We explored age over time, developmental age, and that was the second example today. Again, cross-sectional data, but we were looking at age trends. We've used panel data to do that as well. We've looked at age of onset, like I'm showing you right here on the x-axis. And we talked just briefly about historical time. And this is just some rates of co-use of multiple substances from 1976 to 2013. And so, embedded in many of the data sources we have, there is an opportunity to look a little bit deeper, release ourselves from the functional forms of linear trends over time, and importantly, again, the take-home message from today is that we don't have to model outcomes as linear functions of time. They can be non-parametric. And most importantly is that the effects of variables can vary flexibly with time. We shouldn't always assume that there is a particular level of risk associated with X in predicting Y. It may be for, at certain times or certain ages that it is a significant risk factor. Any other questions, Aaron?
There are just a few more. I was just answering a few people, so I wasn't as attentive to you for that last one as I normally am. Okay, so a question about including time invariant control variables in a TVEM model. Mm-hmm. So again, this is another more advanced one. Hang in tight. There will be less advanced ones after this. This is not for you.
So
if I want to control for race, ethnicity, it's not clear to me if I include dummy variables for all categories or eliminate one dummy variable, as I would do in an OLS regression, which becomes the reference group. If I eliminate one dummy variable, how would I interpret the coefficient functions for my variables of interest? Thanks.
Okay, was that 2 questions, or that race ethnicity example is
yes,
controls?
That's it.
Okay,
yeah.
okay.
Yeah, so read that, or do you want to
No, I think there was a lot, I think, embedded in there. So one question is categorical predictors. So let's talk about race ethnicity. And I didn't have time to get into the details, but we looked at e-cigarette use for Black, white, and Hispanic youth, middle school and high school. And you may have looked at that and presumed that there was another racial ethnic category that was left out. In fact, they were not included in the analysis. And so those models were run with 2 dummy variables indicating 3 racial ethnic groups, white, Black, and Hispanic. And so I could fit those regression models with 2 dummy variables included. I can interpret then differences. I could determine from those coefficient functions significant ages when, say, whites and Blacks and Hispanics and Blacks might have different rates of behaviors or different associations at what ages. And so it's just as with linear regression, you would want to code your variables so that you have 1 fewer dummy variables than you have categories in your predictor variable, your categorical predictor variable. So one more question about that, though, that was embedded in there, I think, was, if you just want to control for race ethnicity or SES or whatever, you can put in additional covariates in TVEM, no problem. Interestingly, though, you have, as the analyst, the option of including a control variable in a way that it has just a simple non-varying effect, just a classic control variable, which is an easy thing to do, and no reviewer anywhere would criticize you for doing that. But you also have the option of allowing your control variables to have time-varying effects along with your other covariates of interest. And so neither one is right or wrong, but how you interpret your coefficients of interest, given that your control variables maybe have time-varying or non-time varying effects, I think the burden is on us to, all of us, to make sure we're interpreting things as clearly as we possibly can. Any other questions?
We're not letting you off the hook just yet. A couple more. So this was an important question, I thought, just to clarify this point. We had the question, are there instructions on creating these graphs either in SAS or in Excel?
Let me think. Yes. So let me think. Well, so one thing I will say is in most of our papers using TVEM, check the appendix. We almost always include our syntax in the appendix so that you can, it's meant so that you can take it and adopt it for your purposes in future studies. And I'm trying to think, for Excel, the only trick if you want to produce figures in Excel is that you have to be comfortable enough in SAS to save the parameter estimate file, which is produced automatically for you, but to somehow save it and open it in Excel. So that's the only trick. Once the data are in Excel, it's as with any other figure you might generate for a manuscript. And so I think that's the only tricky thing. Trying to think if we have tips on that. If not, we could add an FAQ on how to import your SAS data into Excel. You can just type a SAS command to save that file as an Excel file, and it will be sitting on your hard drive waiting for you to open it up and make beautiful publication-ready figures. Alternatively, you can produce figures in SAS directly if you love SAS and you're willing to manipulate figures in SAS. Sarah Vasilenko is my colleague, one in particular, who really likes to produce her figures in SAS, and I can't remember if she's ever shared that code publicly in an appendix, but I know that we'd be happy to share it with you.
But in general, the output is the curve, so you don't get the figures of the overlaid curves, but the curves are generated automatically by SAS just by running the macro. So
the coefficient functions that are specified in your exact model, so effects of x, y, or x1, x2, x1 times x2, and so on, intercept, all of those functions are produced graphically for you, the analyst, to see. For every model that you fit. So you get an immediate in-depth picture of the questions that you're trying to answer. The question then is, how do you get from there to publication-ready conveyance of these time-varying effects? And you might want to manipulate or interpret interactions. And so you can calculate simple slopes. Age-specific simple slopes is a really good way to interpret interactions. You can do all of that really easily in SAS or in Excel. So we don't have a lot of syntax. So again, we are putting together a book, but it probably won't be out until next year. But that is the kind of tutorial information that will be in there. But meanwhile, we'd be happy to share pieces of code with the users.
So, Stephanie, Can you hear me?
Mm-hmm.
Really are getting down to the end, I promise.
Everybody's been hanging in there. You guys have been great.
Yeah. Still, the great majority of people are still around. So, I would like to ask how to use TVEM to ask proper falsifiable questions. When using a hypothesis like the effect of between subjects factor X will vary over time, the capacity to reject that hypothesis approaches zero, hence giving an opportunity to capitalize on chance. Alternatively, an opportunity to invite ad hoc hypotheses ad hoc hypothesis definition, we expect a greater effect of X at ages 14.0 to 16.5 years. What might be an appropriate way to use TVEM to provide a hard test of time-varying effects?
Yeah, so I teach statistical inference and regression to graduate students in my department, and we spend a lot of time talking about this kind of thing. Not specific to TVEM. These are bigger questions, I think, and TVEM is vulnerable to potential criticisms of inflated error rates and things. So one thing that I should share with the group is that TVEM relies on information criteria to either automatically or the user can manually select their final model. Now, what does model selection in TVEM really mean? It means that you're selecting the complexity of each regression coefficient function. So how many knots are required to capture the complexity in this trend over time or age. And so the model selection procedure is, again, it's either automated or you can do it manually and rely on whatever information criterion you're most comfortable with. But so one maybe weak answer to that question is that if the coefficient function really was not substantially varying with time, you would select curves because of the way that information criteria work that protects you from over parameterizing models. You would estimate basically flat lines. They would be flat lines, and so so that's one potential empirical test. If you have a question of whether a coefficient function increases linearly with time, I would say you're better off fitting you could use TVEM or multi-level modeling, but fitting time invariant coefficients and coding a linear effect of time and testing whether that is significantly different from zero or not. I think what TVEM seems to open the door to is more nuanced hypothesis testing, and I think there are a lot of opportunities for doing very systematic and rigorous hypothesis tests that are less fluid and loose than I kind of presented in the examples today. For example, one could code 0 for adolescents and 1 for young adults, and that could be that could be time varying or not if it's cross-sectional data, and you could empirically test whether an association is statistically different during the adolescent period than it is during the adult period with one clean, very specific hypothesis test. But you'd have to have that question a priori and pose it. I think if we want to think about whether e-cigarette users are more likely to be combustible cigarette users, and we have developmental longitudinal data, well, e-cigarette use is on or off at each time point, and so that's time varying variable, and you could estimate the effect of it in a non-varying way over time and get at marginally is the rate of cigarette use higher for e-cigarette users, and that gets you a I think you've got to get explicit about your research questions and then think creatively about how to code variables in TVEM to test them. The way that I've been presenting it and the way that we do in our most of our papers is more on the exploratory side, but a lot of specific hypotheses could be tested if you have the questions specifically laid out. I'm not sure that was a very specific answer, but it depends.
So 2 more questions.
Okay.
How would you approach the nicotine data if you are interested in daily cycles? Waking, random point 1, random point 2, bedtime.
That's a great question. I mean, I actually have thought a lot about the fact that people are sleeping in between the bedtime and the wake up times. And that's something that we should be more thoughtful about in the future. But regardless, if you had an empirical question or a theoretical reason to believe that craving or the link between mood and craving was going to be particularly important upon wake up, which I actually believe might be the case, and less so in the other time points, then let's think about the data structure for a moment. So you have a quick date, and then people have 4 assessments at time 1, 4 assessments at time 2, and so on and so on. Well, you could code an indicator for whether it was a wake-up assessment or not, a dummy variable that's time varying, and it would be coded 1000, 1000, 1000, and so on. And so again, this is similar to the last response. When I think if you have a specific research question like that, that's a really interesting research question, and you can code it in TVEM and estimate it. And so in that case, you would estimate a non-time varying effect of being a wake-up moment versus a non-wake-up moment. And you could estimate and test that. So that's basically an example of that. And it might make sense to allow that effect to vary during the course of the study as well.
No, you're not at all down to 2 users. You've got 30 people hanging in there.
It says 2 on the screen.
That's the number who have their video totally turned off. So at any rate, so the last question we have, unless I missed one and someone can message me if I did, though we are very short on time here. Should the tests of the multiple parameter estimates by sex that Dr. Lanza just mentioned in her example, in lieu of looking for non-overlapping confidence intervals, be adjusted for multiple comparisons? And so that was obviously earlier in the questioning.
I think the multiple comparisons issue is significant in TVEM. No pun intended. I don't have great answers for this. I think if you come to a study and you have a priori specific hypothesis generated research questions, then I think it's prudent to think very carefully about how you can specify your TVEM to test that hypothesis. In many cases, we have never looked at time or age varying effects in an area of study. We just haven't looked. And in addition, our behavioral theories are insufficient to generate hypotheses. And so I would argue in those cases, these are exploratory studies, and we can interpret age or time periods of significance or significant moderation or whatever, and that those should be put into the literature and put forward for future replication. I feel very strongly that these kinds of models can advance our thinking and advance our theoretical development, our theory development, but that they are in no way from one particular study going to give us the definitive answer that sex significantly moderates the link between height and weight during ages 17.4 and 26.2. I mean, it doesn't work that way. Statistics doesn't work that way, right? It's an incremental advancement in our knowledge. I would caution all of us, I think myself included, from over-relying on the p-value tests again and again and again, and interpreting the p-value at this age and this age and this age and this age and so on. I think if you approach it more from a broad brush stroke, but this is the age range when we see significance in this study, again, it's putting it forward for replication in future studies. But there's more thinking to do, absolutely, about the type 1 error rate in TVEM. But I think it's not a simple answer. It's not a simple story. The fact that information at time t is leveraging information in times prior to T and times post T in building constructing the confidence interval at that time point. I think these are not independent hypothesis tests at every moment in real time. It's not that egregious of a problem. But again, I do think that we need to think more deeply about this.
Okay, well, give me just a second here to check in with the chat. And is there anything else that I just missed? Please don't raise new questions because she has been answering questions for an hour. But anyhow, yes, thank you very, very much for your continued participation. And if you have any questions or feedback afterward, please send us an email. And thank you very much. Have a good day.
Thanks, everybody.